Hello from Dendrite Digital in Santa Ana, makers of the Virtue Data Processor, and ZipBits, the website that no longer exists. So, I have this game console that I'm designing in JavaScript now, and later it's going to work with um, um, Verilog on an FPGA. And I have several instructions already designed, including my patented ALU. And we have right here random boxes. So just to give you an idea of what these are, just demo programs for doing. These are just demo programs for doing just to test out some of my ideas. And then yeah, so I'm doing triangles, lines, boxes, and screen redraws. Get a big rectangle that fills the screen. And so this is the code that's running, and we have some initialization for some constants and some variables. And you can see here, these are instructions for my for the Virtue chip. And we have these right here are done with the ALU, and then I have some others that are repurposing some of the redundant instructions for the ALU. So I have 256 of these possible in the current scheme. I can have up to like 768 possibilities that are redundant in the ALU. It's got a 17-bit instruction set. So 17 bits, 131,072 different function settings. 768 are redundant, so I can repurpose them to do something else. And so these are the little rectangles, the little 16 pixel by 16 pixel squares. And here's the set instruction. That's this one here. It's hexadecimal 12, or actually that's hexadecimal C 12. And so this is the repurposed instruction here, and so I or the different parts together to form an instruction. And so repurposed, specifically the set, and then we have the X register. Yeah, see, these are the registers. We have 6 special registers, followed by register A through Z. So it's 32 together, altogether. So program counter, stack pointer, carry history, overflow, remainder, and random number. And then the rest are just single letter A through Z. And then, ALU instructions in this form. These are repurposed functions. And then this is the thing. This is the program with my Virtue chip that is drawing those 16 pixel by 16 pixel rectangles. Here's the program for doing lines. You can see I'm using a random number a lot, random number generator a lot, and then triangles. Here's my instructions for doing triangles. And you'll notice that these are ALU instructions, not the repurposed ones. The or and not repurposed. They're done with the ALU. And then when box, see, here's box. When it's called, this is the machine code instruction that box does. And then we have decrement, divide, get, increment. See, we can increment by up to 1023. So maybe I'll add one to it sometime in the future so that there's not a no-op sort of situation. But I thought this was less confusing for now. Jump. Yeah, just jump to some other location in memory. And then jump to subroutine. So you push the program counter on the stack, and then you decrement the stack pointer. And then line. This is what's going to be in hardware. A single instruction for line. It takes the parameters out of the three registers specified by the instruction code. Yeah, see, the top 5 bits are the color. The next lower 5 bits is you can see I'm taking both X and Y out of that. Yeah, X is the 12 bits, or Y is the low 12 bits. X is above that, and I'm going up to 4096. I didn't think I could do any higher than that. And then same here, 12 bits for the X, 12 bits for the Y2. And that's coming from so top 5 bits color, next lower 5 bits 0.1, and then the last 5 bits before the instruction is 0.2. And here we're just converting them from big int to number for the coordinates here. Yeah, these don't operate with big int, so I scaled it down. So that's how you draw a triangle or a line, and then multiply. I'm doing unsigned multiply. I suppose I could make another repurposed instruction to do signed or floating point or whatever, but this is just integers for now. And then here's the null instruction. I have this so that if I ever try to call something that hasn't been implemented, it'll print it out in the console on the screen in the debug. and put. So this is like get in reverse. Um, so you got the three 5-bit segments, and then one is used as a register address for the address, and two is used for a constant add. And if the address is 0, then less than 0 it equals 0. If it's max RAM, then it equals max RAM. Greater than or equal to max RAM, then that equals, yeah. So I'm just setting borders on it to keep the data small. Eventually, it's going to go on an FPGA, and the BRAM is kind of limited on it. So then, if 1 equals 1, which is the stack pointer, I should probably put stack in there instead of the 1. And if there's no offset from the pointer, then you decrement it. And then we set the memory address, or set the memory to the register up here. And then pixel, we have getting the color of a pixel for here. And then return from subroutine works kind of similar to push or put. And then set is just getting a 10-bit number and putting it in a register. And then shift left. See, I'm using the overflow register for this. So at first, yeah, I shift left into A, shift A to the left, and then yeah, see, we're putting it in the overflow. We're putting the low 30 or the high 32 bits in overflow, and then we're clipping it and putting it into the specified register. Then shift right, same thing except going the other way. Then triangle. Yeah, I have 32-bit registers, and for triangle, the 3 segments, the 3 5-bit segments for the register specification. You can take whatever register you want, and then each one has a point, X and Y location, and a color. Is the high byte is the color, and so since I have three points, 3 colors, red, green, and blue, I have to parse it out just right. Works out just right for use for a triangle. And then here's that ALU that I talked about earlier, the patented ALU. So you can see it's doing it, bit by bit. But in Verilog, I have a way of accelerating this. And then here's the ALU and the reverse direction. And so here's the repurpose functions. You can see I have a lot of nulls in here. There could be like 3 times this that I could repurpose. And so this is the first 256 of that. And then here's the main loop, the run segment, and we go through and we get the random number. Initially, I'm changing the random number on every cycle of run, and then here's code, which is here's code. Which is the instruction that you saw me parsing everywhere. See, there's code everywhere in these subroutines. And so you get code from the program counter register. You use the program counter register to get a memory location and put it in code. And then register program counter is incremented. And here we're testing if it's a repurposed function. And then here's the low byte of code as an index into the repurposed instructions here. And if it's not a repurposed instruction, then it goes into the ALU or the ULA, which is just the reverse carry bit. And yeah, make random number color, key down. I'm going to change this to be another instruction to try to I'm going to use it as another instruction to try to I haven't put this in a repurposed instruction yet, but I will. And then prevent default event update, which goes through run 80 times on every 20 milliseconds. And then here is just initializing the recs. I don't think I need that. Maybe, I don't know. Yeah. So yeah, that's the principles in a nutshell of what I'm working on to design my game console in JavaScript of all things. So let's go back to that. Let's go back to that. See what we get. So there's boxes, lines, and triangles.